Hello, my name is Nakam Mutedi, a computer science student here at Macquarie University, and I'm going to present about our proposal for our computer science project or final project under the topic multi-agent visual storyboarding for accelerated refugee education, competence-based content authoring. So this project is not just AI, but it's fundamentally a computer graphics and visual programming system for education. So visual storyboarding clearly indicates that our system will follow a graphics pipeline, use procedures in generation, and also produce animated-ready assets. And then the multi-agent part of it means that our system will use different specialized models, for example, a curriculum mapper for text processing, a storyboarder for graphics planning, and an image generator for diffusion graphics, and also a video composer for visual programming. So basically, we intend to create a graphics-driven content authoring tool, not just a text generator. And then under this topic, we have some keywords. One, we have computer graphics, which is a field of computing that focuses on creating, manipulating, displaying visual content using computers. First, it involves generating images, animations, and visual simulations through mathematical models and algorithms. For example, 2D, 3D modeling, rendering, animations, image processing, visual effects, and more. And then we also have visual programming, and it is a programming method where developers create programs using graphical elements such as diagrams, flowcharts, and in this case, we may encounter features like icons, blocks, connections, among others. So then we also have competence-based curriculum, which is a learning approach that focuses on mastery of specific skills and competences rather than just covering content. So in this case, students progress by by demonstrating their understanding and ability, not just the time they spend in class. And then we also have generative learning technologies, which are AI-powered tools that create educational content such as quizzes, lessons, or even explanations. So this one helps to personalize learning by adapting the materials used for learning to each learner's level. And then we also have interactive storytelling, which is a method that uses stories with user participation to enhance engagement and learning. So here, learners can make decisions that affect the story's outcome, improving critical thinking and retention. And then we also have multimodal AI, which are AI systems that combine multiple types of data, that is text, images, audios, and videos to understand and generate richer outputs. And then we also have refugee education, which is education that is designed to meet the needs of displaced learners who face barriers like interrupted schooling, language challenges, or even lack resources. And then lastly, we have vision language models. And these are basically advanced AI models that link visual and textual understanding. They can interpret images, they can describe them in words, or even generate images from text. So that brings me to my next slide, and this one contains the contents of our presentations listed down as you can see. And then allow me to go to the introduction and motivation. So first of all, over 387,000 refugee children are enrolled in accelerated education programs with challenges like limited resources, language barriers, trauma gaps, and some of the gaps in the accelerated education programs are that these educators have to create graphics and learning media manually, let's say drawing with bare hands, to make students understand. Yet to some extent, they lack skills in 3D modeling, visual programming, and also content design. So we find that visual learning content, which is essentially the competence-based curriculum, requires skills in 2D, 3D modeling, motion graphics, video production, and more, which these teachers do not have, and therefore cannot manually create graphics and animations because they lack those skills. And then the fact that they lack resources and the resources that they have, let's say the books are mostly outdated, adds on the gaps and challenges. So this is where our proposed system comes in play, and it introduces or proposes an AI-driven multimodal content authoring system, which solves these issues we've talked about earlier by automating graphics, automating computer-generated imagery using vision language models, generative graphics, speech and lip sync, and visual programming. And it goes ahead to like generate CBC-aligned visual lessons, animations, even storyboards. So basically, computer graphics makes the abstract CBC competences visible, concrete, and also engaging, which is essential for the refugee learners. And then we may ask ourselves, why graphics? First is to enhance understanding. This is in the sense of converting complex data, concepts, or even environments into clear visual representations. Then another thing is to improve engagement. It's because visual rich content like images, animations we talked about, simulations, they keep learners and users more engaged compared to text-based content. And then the other thing is that it supports realism, like through enabling realistic modeling, rendering, and animations, which are useful in education. And then lastly, it's for better education. This is in such a way that the visuals, they convey information faster and more effectively than when we use text alone. So that brings me to our next slide, that is related works. So when it comes to the related works, we're able to review some papers basically in recent years, like you can see in the table. And then we're looking at different models, their contributions, the architectures, and most of them were to do with taking in text, images, and then generating captions, descriptions, images again still, and even videos. So this other slide is also having related works, and we also looked at the problems they encountered, which included memory constraints or high compute, quality issues, and more challenges that are included in the table. So most of these papers related to our project, as they were in like the same grounded in graphics-based learning, like graphics-based learning systems, also grounded in generative media technologies, visual language, AI, and also multimodal storytelling. So we intend to extend like existing systems or models by adding automated graphics generation and also culturally adaptive visual programming.
So starting from where my colleagues stopped, introducing the problem statement. So the domain specific and the computational problem. So Uganda, as we all know, is home to over 1.5 million refugees, and of these, we have about 387,000 children who are enrolled in school, but they lack access to high quality education and learning materials. So the existing material for the AEP and the CBC is outdated, linguistically mismatched, and unavailable offline. So by the AEP, I mean the accelerated education programs. These are programs which are aimed to help students to take a short while at school. Students who have been affected, like learners, like refugees or people who dropped out of school for any other reason, and the time they come back to school, we help them. These programs help them take a shorter while in school. So if you're supposed to do O-level in 4 years, this accelerated education program, make sure you do it in about 2 years. And for CBC, which is competence-based curriculum, this is one which aims at it majorly focuses on what a student can do at the end of the syllabus, not what they have memorized. So the contents of these materials is always outdated, linguistically misaligned, and unavailable offline. So as you know, when a refugee settlement, you have students from different walks of life. and different backgrounds. Some of them, their first language is not English, and the others, it is Arabic, French, depending on where they came from. So from those who come from Sudan, it's Arabic, and those who come from Congo, it is French, and they come here to those who came from other parts of the world, and it's English. So it is always misaligned, and there's limited access to the internet in refugee settlements, which worsen the education gaps. And the computational problem lies in how are we going to provide a tool that is curriculumly aligned to the content that it generates is curriculumly aligned, and it has multilingual support where we have cultural adaptation and also make it available offline. That is where the computational problem lies. And so for our problem statements, we came up with research questions that guided our work, and research questions and objectives which helped guide our work. And the research questions were how can a graphics-based content authoring framework support CBC-aligned learning in refugee education? Then what methods can generate multilingual, culturally adaptive and interactive learning modules that function both offline and in low bandwidth settings? Then how effective is AI-generated graphics and interactive content in improving learner engagement, comprehension and retention in refugee contexts? And how can open access visual learning objects and templates be designed for scalability and reuse by educators in NGOs and in fragile settings like refugee setting, the refugee settlement, of course. Then our main objective for our study was to develop an offline fast modular graphics content authoring framework for the CBC aligned learning modules. And also what we hoped to obtain, like our specific objectives were to create animated and interactive learning modules using lightweight open source platforms, and to evaluate learner engagement, comprehension and retention in refugee education settings, and to produce open access visual learning objects and templates for educators in NGOs and other settings at a scale. So the scope of our study, we were able to develop a system to generate structured lesson scripts for the CBC aligned topics. And we also implemented an evaluation framework for assessing the script quality, the topic alignment, and resource relevance. So in our code, in the notebooks, we had an evaluation technique to help us assess the script quality. So when the first agent generates the script, we were first given an option of first assessing it to see if it is like aligned to the topic and is it relevant, and readability metrics, and like because the script is like the foundation of the storyboards, then to the video and all that. So we will first assess the quality of the script because it affects everything. And so we had a prompt to either accept the generated script or reject it and regenerate something new. And then we also prepared and structured CBC aligned topic datasets for lesson planning and automated content generation. Then we provided data-driven insights into the script coherence, topic coverage, and engagement potential to guide the future multimedia lesson development. And so the significance of our studies, I would say we helped it improves refugee access to quality education, number one, for the learners, and then we support teachers with automated content generation, as it is simply a prompt. Teacher simply prompts and everything is automated, from the script to the storyboards to the combination of the scenes to the last video. And then we promote SDG4, which is quality education and advances in artificial intelligence in educational research. Thank you. My colleague will start from here.
Hello, my name is Sinata Mallory, and I'm going to take you through the research methodology and the system architecture of our project. So this is a multi-agent system architecture, meaning that it's we fine-tuned multiple agents to produce the results. So at the start, we have the curriculum agent. This one maps the inputs, the prompt, the user input in relation to the curriculum and the competences. Then we have another agent to generate the storyboards. So this one creates the scene plan, and then we have the visual agent that generates the images, and then we have the narration agent that produces the audio, and then the final one that combines everything into the final video. So each agent, its output is the input of the next agent. So let's go into details for this one. So we start with the system architecture. So when the user inputs a simple prompt, we get the first agent gets that prompt and maps it using similarity layers and then transform encoders to align it with the curriculum. So we get a curriculum aligned prompt, and then that prompt is fed into another agent to generate the script and the storyboard. So that script is then forwarded to the graph that is to like culturally augment the script, like to put in cultural content with our local, like to make the agent more local. So that's now that script that is now locally aligned is forwarded to a storyboard generator, and this one generates a simple script that is going to be used by the denoiser here to generate the storyboard frames, and then from this storyboard generated script, we're also going to generate the audio. So these storyboards are then later, like you see this is to come back and see whether the images generated align with the script very well. So once that is achieved, we forward these storyboards and then the audio to the video composer. This one combines both the audio and then the frames into the video. So we have here the lip sync encoder. This one, what it does, it aligns the facial encoder, like the animation, the way the mouth is moving, in line with the audio, and then all that is forwarded to the lip sync generator to generate the final audio with this final video that was generated. So and then you get the final video. So some of the agents that are being used in our system architecture is the SDXL. So this one generates the images. So it uses the prompt from another agent to output the image, and then we have Google TTPS. This one generates the audio. Still, it also uses the prompt and then to generate the audio. We have the mini LM large language model. So this one helps us to generate the script. It generates the script that is going to be fed to the SDXL to generate the image. And then the Wave 2 sync, this one generates the lip sync, like it gets the video and make sure that the lip animation is in line with the audio. Thank you very much.
Hello, I'm Suko Benjamin, and I'm going to be taking through the preliminary results and the associated data analysis. So to start off, let me start with explaining our data source. So we wanted to first create a script that was curriculum aligned and competence-based, because our script was going to dictate whatever was going to come out of our pipeline, the story that was going to be created, and the visuals that were going to be created were all going to be determined by the script. So we wanted the script to be curriculum aligned. So we went to the NCDC website and we were able to acquire a curriculum for a given subject, then we extracted the relevant fields, the fields that we felt like were going to dictate our goals, then we extracted them into an Excel file. Then that Excel file was then used as our data set to test out the scripting process. So we decided to choose mathematics because we felt like if we were able to succeed with math, if we test our system on math, the pedagogy, the relevancy, the ability to bring out all the explanations, the other subjects will be relevantly easier. So we chose to start with mathematics level 1, term 1. So the accepted education program is divided into two levels, that's level 1 and level 2. It's different from the standard curriculum. So there were 17 topics in the level 1, term 1 curriculum, and there were 12 columns, which were our features. So as I said, the target was to create computationally aligned, competence-based, and curriculum aligned. But we needed to also mind the pedagogy, because when teachers are teaching or when lessons are being held, the pedagogy matters. Some lessons are story-based and story-based, and some others might choose examples, question approach, depending on the type of topic and the objective. And a subject might have topics that require different pedagogy approaches. So we wanted to achieve all these. So these were some of the columns that we had in the dataset, that we have in the dataset. And some of the standing out columns that were really useful in our objective included the competency, the learning outcomes, then the Bloom's tags. They were not necessarily Bloom's tags, but they were an hybrid of the Bloom's tags. They were cognitive skills like tags to show which cognitive skill is required for a particular objective in the curriculum. So topic, then objective, then the tag to further help the teacher know how to approach or how to deliver the lesson to achieve that objective. So we used the combination of all these to guide our LLM to create a really perfect script that helped us achieve what we had set out to achieve. So let's move on to the EDA. So in the EDA, we first sought out to analyze the learning outcome tag frequency. How often do these tags appear in the different objectives? Then we also looked at how often do these tags appear together on the same objectives to try and know how they correlate with each other. Then we also analyzed the number of topics in that curriculum, plus the activity count per topic, to try and see the activities, because through the learning outcome and the activities, the competence of the learner is analyzed. So we wanted to see all that. Then the duration versus the outcome density, the suggested duration of the lessons, plus the outcome stated in the curriculum. I wanted to see whether that correlated, how that varied. Then also the narrative density per topic. So this was useful because our system has to be resource efficient, and the LLMs have this constraint of context window. So we wanted to see how huge each particular topic would is. So the narrative density of each particular topic. So that was basically the simple idea we carried out on that small dataset we were able to create. So this dataset was created to aid in the script generation. The other datasets that are to be used in the fine-tuning processes were not yet fully acquired, and the idea was not carried out. So allow me to move to the preliminary implementation evidence. So what has been done so far? So as I said, we constructed the CBC-aligned pilot datasets, a sample to see how best it worked out for us. Then we extracted competency learning outcomes sequences, basically the fields in the curriculum, and put them in the dataset. Structured syllabus content into machine-readable format, automated processing. Then added system feasibility tests, so automated curriculum mapping, lesson objectives, and activity sequencing. So what we wanted to achieve, this was if you get a prompt, if the learner prompts, because the system has to be the way you set ChatGPT. You prompt the system, and the system generates a story out of what you're prompted to teach you from your request. So from the prompt you give us, we have to map what you've requested with the relevant topic in our data set from the curriculum. That's the automated curriculum mapping, then lesson objectives. Then from there, we then analyze what do we want to achieve based on the topic that has been mapped to your request. Then the activity sequencing. What then should then be done out of the objectives we have found out? What then should then be achieved? What shouldn't be missed? So then the generated lesson scripts and visual storyboards. So from the scripts, we then go to the storyboards. So the scripts help us to generate the narrations plus the visual descriptions. Those are the storyboards. Then the visual descriptions then move on to the generation of the images themselves, the graphics themselves. So verified pedagogical coherence, CBC alignment. So we verify that with the use of the dataset from the curriculum, we're able to achieve this, plus the other tools I talked about. So the graphics-based preliminary results produce scene-based visual lessons, and I'll visually demonstrate this in the next slide. Sorry. So these are some of the graphics that were generated for math. So here, the learner prompts the system that they want to maybe learn how to divide. Then the system uses the learner's prompts to then generate these kind of visuals. Then the other, that's it. So moving on to the data and tools, data sources, as I said, the CBC curriculum documents, AAP learning guides, open educational resources. So on top of the curriculum, we also need the textbooks, because we cannot assume that the LLM we're using is fully aware of how to maybe, for example, teach number bases, the topic of number bases. So we want to ground it on a particular textbook, a proven textbook that has the relevant content. So it will, based on the curriculum plus the knowledge from the textbooks, from the relevant textbooks, to come up with the actual perfect script. So then, the technologies use Python, JavaScript. We have to use because this is a proposal. You'll forgive me, some of these are not yet implemented, but because we're proposing this Python and JavaScript. So this will include the machine learning processes, the scripting plus the visuals, the visual language models, the fusion models, then text-to-speech engines for the narrations, expected outcomes. So expect an interactive, visual rich learning content to be produced, improve learner engagement, reduce teacher workload, scalable offline deployment. But this has proven to be one of our most challenging objectives, because currently the LLMs and the workflow demands a lot of hardware resources, but we are working to make sure that we achieve this outcome. Then support for inclusive education. So this will have to do with integrating it to be multilingual. I think it can also be to help a lot of many different types of people. So the evaluation criteria included the technical evaluation, that's the generation time. Currently, from the test we had, the scripts took a lot of time, around 15 minutes to be generated. That's one script for one particular topic. So we'll based on that to evaluate our projects at the end. Then resource usage, as I said, offline reliability, where the tool can run on edge devices. So education evaluation, that's data alignment, teacher satisfaction, learning engagement, cultural relevance. The sense generated relevance to the learner's environment. In conclusion, the study addresses the challenge of limited access to engaging competence-based learning materials for refugee learners in various environments. So we set out to create graphical materials that can aid learners grasp the topics better by leveraging generative AI and contextualizing the outcomes to the learner's environment such that they can easily relate to the materials. So the tool will make it easy to generate such content, and it bridges advanced AI technologies with real-world humanitarian educational needs. Thank you so much. That has been our project proposal.